Okay, I think we're recording. So here's the problem. We have a bar of charge of total, a bar of charge is total charge of Q, uniformly distributed, has a length of L, and a proton with a charge of plus E is placed at a distance Z above the bar. The question is, what is the force acting on the proton? So we've seen problems like this before in recitation. This is going to be very similar to, I believe, worksheet 1, problem 2, and worksheet 3, problem 1. So how do we approach this problem? Um, we're going to need to find the force is the electric field. So that's the bulk of the problem. So the first thing we're going to do is to solve the electric field. And the way we're going to do that is the following method. Step one, we're going to use symmetries to try to figure out what parts of E we need to solve for. Then we're going to set up the integral for the E component that we need, because hopefully we only need to solve for either EX or EY. And then finally, in the integration, we're going to use our knowledge of charge distributions to set it up in a way that we can solve. And then yeah, finally we'll plug it into the equation, F equals QE, to find the force. So let's start with step one. We have our bar of charge that we're going to center about 0. I think this is the easiest way to approach the problem, which means the ends of the bar are at minus L over 2 and plus L over 2. Now let's imagine this bar, not as a bar, but as like a bunch of little tiny particles. So I'll draw maybe these in green. Like in reality, we can imagine this is like a bunch of really small parts of like charge, some amount, we'll call it dq. That's all spread out about this bar. Now, what's the electric field contribution from some point right here? If we imagine this as a small point particle, we know from Coulomb's law that this will give me some resulting force pointing this way, right? Positive charged bar, Q, positive proton, E, it'll push it out in some direction. If we look as if we're in a mirror on the other side, there's going to be another corresponding charge over here. I guess my drawing is not fully accurate, but another piece dq here that'll give me the same exact magnitude, the pointing, effectively mirrored about the center. Now, if we break apart these two vectors in terms of components, you'll notice that these blue arrows in the x direction are going to perfectly cancel out. So by using this argument, the claim that we're going to make is that although this is the general form for our electric field, due to symmetry, Ex is equal to 0. Therefore, we need only solve for the y component. So that's our first step. Our second step is now going to be to set up this integration. So let's think about this a little bit carefully. We know that EY is the integral of all of DEY, where DEY here is like the infinitesimal parts of the electric field that are being applied from like all the different charges on this rod. Obviously, this is very annoying to work with. So if we examine our photo again, or image, let's consider some slice here. I'll call it dq. Here's our proton. The net electric field will be some component that goes like this, right? But if we only want the component that goes upward, maybe not that angle, but this angle over here would be better. Call this angle theta. We need the sine of that angle because that'll give us this component here, which is exactly the same as the green arrow I drew to the right. And now we can write this in terms of the total electric field, because if this is some component here, dE, then dEy is this component pointing up. So we haven't defined an angle, but we can make the following argument. I know that this height here is Z. Let's call this length here X. This is going to be the variable that we sweep over. Then this length here should be x squared plus z squared. Since sine is equal to, I'll write like rise over hypotenuse, this is equal to z over x squared plus z squared. So now we have the first steps to our integral. So from here, now we can start a process of setting up this integration. So we know that EY is equal to this integral. And now we know from Coulomb's law, dE is equal to k dq over r squared. Just for some clarity, k is also short for 1 over 4 pi epsilon naught. And r squared is the distance squared between the point and source. So in our case, we can rewrite dE is equal to k. R squared is going to be x squared plus z squared squared. I'm going to get this way for a reason. We'll see later. dq. Because the distance, as we saw up here, between this small slice dq and the point is the hypotenuse of that triangle that I drew. So now what about dq? Let's look again at this little slice up here. And I'm going to make the claim that dq should be proportional to the length that I am looking at. So this distance here, let's call this dx because it's some differential length. And if lambda is a charge density, we get dq is equal to lambda dx. This is because we take like this little length of charge we're dealing with multiplied by the charge density. And in our case here, lambda should be equal to q over L because this gives us the charge per unit length. So in that case, we get dE is equal to k square root of x squared plus z squared squared. And now dq, I'm going to write in terms of lambda actually, just to keep things simple, lambda dx. So now we can make our substitution integral. K lambda over square root c squared dx. And before I set the bounds, I'm just going to simplify this a little bit. There should be squared here, sorry. So our integration measure here is dx. So anything that's not related to x, we can get rid of, or at least pull outside of the integral because they're constants. So k, lambda, and z are all constant. We get this integral of x squared plus z squared cubed. And now for us to set the bounds should be from minus L over 2 to L over 2. Why do we do this? If you remember our bar, we need to sweep from here all the way to here so that we can account for every single value across this bar. And we centered it at 0, so we go from L over 2, minus L over 2 to L over 2. I will mention this is the easiest way to do your bounds. And in any of these problems, you can always shift it so it's set up like this. But there are also problems in which maybe you're not centered. Like for example, this is 0 to L. And in that case, really the only difference you have to make is, let's say this is X. This length here, if this point right here is like L over 2Z, in terms of X, this distance should be square root of Z squared, because the height doesn't change, plus, and then here I would write like L over 2 minus X squared. And you'll notice this works because when X is L over 2, when it's right in the middle, the distance is Z. When X is 0, you get a total length of L over 2. And when x is L, you also still get a total length of L over 2. Just be very careful about where you define your coordinate system. But anyway, back to this integration. So this is an integral that I don't know off the top of my head. In recitation, I said that this is something that you would just be given. And also, this problem is actually on your formula sheet, so maybe you don't even need it. But the integral given, this should be, I believe, x over z squared, x squared plus z squared to the 1/2. So square root of that, and then evaluate it at the bounds. So now it's just a matter of plugging this in. I'll pull the z squared out here as well. So I've taken this and I put it out here. When x is L over 2, I get L over 2 over square root of L squared over 4 plus z squared. Minus negative L over 2 over the same denominator. We'll simplify this a little bit more. I now cancel out one of these z's. I'm going to pull out the denominator in the front because it's the same for both. And then L over 2 plus L over 2 is just going to give me an L. So this is E in the y direction. I want to make a quick digression before I keep going to point out that this is the same as the formula that you would have gotten on your formula sheet. So if you look at the formula sheet that you're given, you're told that like E over the center of the rod is equal to, and I'm going to change the variables to match the ones that I'm using. 1 over 2 pi epsilon naught lambda over z, 1 over the square root of 1 plus 2z over L squared. So I'm going to move this around to show that it's the same answer that I got. So first, this term here, this is the same as 2 times k, because k is equal to 1 over 4 pi epsilon naught. And then what I'm going to do here in the denominator is I'm going to expand it out to write it in terms of the term squared. So 1 plus 4z squared over L squared. I'm going to multiply by square root of L squared on both sides, top and bottom. So I get an L on top, and then here I get L squared plus 4z squared. And then I'm going to multiply by square root of 1 over 4 on top and bottom. Let me put this in blue so it's not too confusing. And that'll give me this 2 and the 4 will cancel because square root of 1 over 4 is just 1/2. And then I'm going to get a square root of L squared over 4 plus Z squared. And you'll notice that these two are the same. Add another page. So therefore, our electric field is given this E component in the Y direction that we have, or K lambda L over Z, times the square root of L squared over 4 plus Z squared, Y hat. It's very important that you specify the direction of your vector, because this is a vector at the end of the day. So great. So now we need the force. So F, this is the easy part. F is equal to QE. This is a formula that you're given. Now we know the charge is plus E, because that was given in the problem. And then E is just K lambda L over Z, 1 over square root L squared over 4 plus Z squared times y hat. And you'll notice that this force and electric field both point straight up. And I think this makes sense because by default, we have lambda is equal to Q over L. You'll notice that if we change Q from positive to negative, it actually flips the sign to go downward, which makes sense because then they would attract. But otherwise, if everything is positive, this electron should just go straight up. So once you've done this problem on your own, I have some suggestions for additional problems you can do. So one problem to try is the offset bar. What is the electric field at the point Z above the rightmost edge of the bar? As a hint to do this, you basically set up a lot of the same problems that you did before, but now I would set this end here to 0, this end here to L. And the thing that you're gonna have to try to figure out is I'm drawing all these lines from like little parts of this bar, right? You're gonna have to figure out what this vector or this distance R is for each of these little like differential charges. The second problem, which I sort of alluded to, is non-centered bar. How would your integration change if instead of going from, so previously we went from minus L over 2 to L over 2, how would you change how you did the integration if you went from 0 to L instead? And then my third question that I would suggest you do, which is very similar to what we did in recitation, is just the case of many bars. And I would do as many configurations as you can. Just take as many bars as you can and figure out what the electric field is at different positions. So maybe A over here, B over here. And for problems like this, you could use the formula sheet to look at the electric field and just use principle of superposition, but definitely build some comfort with these ideas.